Hey everybody, and welcome back to Fastware. So just want to remind all the viewers that I'm gathering suggestions on the topic for a longer series to do. There are a few suggestions already to do a memory allocation, a series on memory allocation, writing custom memory allocators, to do a high performance logger. One of the viewers suggested to do an in-depth look into coroutines and in-depth as in assembly level analysis. So if you have any suggestions that you would like to see, please write it in the comments. I read them all, respond as well. Like the video, subscribe not to miss it as well. And with that, let's dive into our today's topic, which I just want to have a look at a standard containers that a C++ standard library provides. Obviously, we all use it. It's sort of a common thing that any C++ application will involve standard library containers. But many people don't understand the performance and the scaling of these, I think, in depth. And therefore, I see many parts of the code littered with maps, lists, sets, where usually there is no need to do that. And I'll explain why. So as usual, I write a little benchmarks to demonstrate each different thing. So I have a vector with no reserve, which just takes data and then pushes back. Next is to do a vector pushback but with a reserve. And the next one is to do a vector insert, which is reserved the vector, but then we're inserting somewhere in the middle. So just take the size, divide by 2, and then insert it. So obviously this will move half of the data out of the second half of the vector, move it by 1 in order to make space to insert it. Right? So the next container we'll be looking is a list. So we'll do a list append and prepend as well as insert. We will do the set and we'll have an insert, just a value, and then insert as well somewhere in the middle. Do the same thing with the unordered set, and then do exactly the same thing with a map and the unordered map. So I think we need to have a look how each of them are implemented. So a vector is a contiguous piece of memory, right? So once vector runs out on pushback, it says, okay, so we need to reallocate. So we reallocate to a larger size with a scaling factor, and then continuously add to the same continuous memory. Now, a list is a node-based container, means each of your elements that you're inserting are going to be allocated separately, right? Unless you're actually implementing your own allocators on top of your container, this is the standard behavior. And a list in C++ in the standard library is actually a doubly linked list. So that means it has a pointer previous and a pointer next. And they're tied together. So each allocation can reside anywhere in memory. So as you can understand, once you need to iterate through the list to find the next element, you need to look into the next pointer, dereference that, and then jump to some other memory location, then do exactly the same thing again, which is incredibly slow due to that it causes a lot of memory cache misses because you need to dereference that. The vector doesn't suffer from that because it's a constant kind of offset from the kind of a data point, right? Now, a set and a map, I'll kind of group them together. They are the sorted containers. They are node-based containers implemented in the concept of the red-black tree. And I will show you how red-black tree works later on in the video, so bear with me. And the last one is actually the unordered set and unordered map. Both of them uses a hash table and then a linked list, kind of a map of a key value pair or just a value So we hash the key, and then in the set we'll insert a key into the linked list, the actual value, so we can deal with the conflicts. And the unordered map has a key value parent. So, and it's sort of like a bucket of data, right? So those are going to be the containers that I'm going to be looking at today. And as usual, I have a performance benchmark that I wrote. So I'm going to just run it, not look at it in depth of how it works or why it works. Just to want to give you some good notion of what is the scaling and the performance of these containers at different scales. So as usual, have 100 elements, 1,000 elements, and then 10,000 elements that I insert or append or prepend in the loop. And then that gives me a good scaling factor so I can understand how these containers perform. So it's a long list. We keep running. I'm going to be finished anytime soon. Here it is. So what we can see, the vector no reserve takes about 147 nanoseconds. The reserve, that's for the 100 elements, right? Reserve is about half of that. However, if you look at, for instance, inserting into set or list, let's say this is the append and prepend, right? So these are about 10 times or 9 times slower than vector without even reserving. And this is an important thing because when you insert into the vector, you just, like when you add it to the vector, it just goes to the end of the vector in, for instance, this no reserve case. With a list, you have to model pointers next and assign the end pointer as well in the list itself. That is very costly. So I have prepared a little graph so we can have a look at this. So this is the actual data that I collected with several runs, accumulated, and computed this data set, which is just the number that we have here. So this vector is 145 nanoseconds divided by 100. That gives me 1.45. And then, so 633 divided by 1,000, that's 0. And this is just to give an indication of scaling. And obviously, so I could graph it because otherwise the numbers are so huge that everything looks like a vector, looks like a straight line, like there's nothing happening here. Inserting more and more elements, we can see that actually the map and the set really become very slow. So it takes 91 or 88 nanoseconds per insertion to perform this operation, which is just terrible. And I want to demonstrate why that is. So here we're coming back to this caveat, how the map in a set is implemented as a red-black tree. So the red-black tree, let me just switch to a, oh, there we go. So this is the red-black tree simulator. You will find a link to this in a description below, so please check it out later. Play with it. It will give you a great understanding how it works. So let's say we start by inserting a value 100. Here we go. We inserted the value 100. Now let's start by inserting next value, which is 80. So we inserted value 80. Great. So now let's insert value 20. So it keeps adding, but then this is the tree rebalance operations, which all these pointers need to be reassigned what belongs to what, and mark all the nodes as a red or black. As we continue with that, you will see that the tree rebalancing operations are actually causing quite a bit of lag, and there's a lot of motion within the tree, which doesn't happen, let's say, even in the list or a vector. So if we'll just continuously add. So you can see a lot of motion here. Let's insert 90. Let's insert 10, 50, 70. That's not how you would probably think that this actually map, or set in this case, would look. But that's the operations that it actually performs. So let's insert 75 and see what will happen now. So a lot of repositioning, a lot of restructuring of the tree. As you can see, the entire tree got rebalanced. So, and that rebalancing of the tree, because it's a node-based container, so again, it has this left and right pointers. It needs to dereference in order to access the next node. And then you need to iterate pretty much through the entire map to rebalance this entire map. These traversal operations on sets and maps when inserting or just appending are actually incredibly slow. Therefore, for any serious implementation, for any serious high performance code, I would actually recommend not to use it ever. So sets and maps, no, I wouldn't recommend doing it. I would recommend using a vector and then building in, ordering and inserting yourself. Because let's go back to our insert. So these are the insert in the middle operations that we do. So we just pick out the iterator somewhere in the middle and then we insert it. And then you can see that actually, so obviously unordered sets and unordered maps will not be affected by this. However, doing that for something like a vector, while it is much slower than anything else, like when it was actually just pushing back, it is still fast enough so you can build associativity into it. So you can do a binary search, you can insert in appropriate place, and then you can continue. And this is, I think, a great pattern to build vectors into sort of a set, because a set is just, it's poorly implemented vector which is sorted. That's all it is. So I hope that you learned a little something about standard containers and see that actually maps, especially sets, are terrible to be used in any high performance code at large scales. I would definitely recommend unordered sets, unordered maps if you ever have such a requirement, which I don't believe there is one, but maybe you have. But for anything else, use the vector and build any abstraction that you want on top of the vector. That will give you the best performance that you can possibly can. And always remember, measure your implementations, benchmark against actually the standard library so you know that your implementation is faster in your case. And with that, thanks again. If you can, like the video, subscribe, and I'll see you next time. Have fun writing fast code. Bye!